Welcome to the last video on equilibrium. Today, the last one we're going to look at is tension equilibrium. So stuff that involve tension equilibrium. You may say, hey, we already looked at the rod hanging there. Isn't that already tension equilibrium? Yes, but this one is double tension. So tension times 2. We're going to see what that means. A quick recap on what tension is. It can be in a rope, a string, or an object compressed or pulled. But most commonly, we're going to look at strings. So let's say this guy's pulling with some force. It's going to cause a tension like that. So let's say we cut out one mini little section on the rope there. That small piece of the rope is going to experience some force pulling to the right, but also some force pulling to the left. Why is there a force pulling left? Oh, because this other guy is also holding it, exerting a force. So basically, if you cut off the whole rope into mini sections everywhere, every single section will experience a force to the right, a force to the left, force to the right, force to the left, force to the right, left, right, left, right, left. And eventually there's too many arrows, so we just say, okay, tension is just spread out throughout this whole thing. Spread out, so-called spread out. Which means, if you have a pulley or something in between, tension will be the same on either side. Okay, that's what we looked at. If you have pulley, no friction, and you pull like that, tension is the same. Okay, if you have an object hanging, the object will experience upwards tension force. That's what it means lah. Straight out this whole thing. So let's take a look at what are the kinds of tension-related questions, tension times 2 questions in this chapter. First one is about a picture on the wall. Picture on the wall is supported by a wire loop over a nail. The mass of picture is that weight. What is the tension supporting the wire? Look around your house or where you are. Are there things hanging on the wall, hanging by a string? If there is, it's pretty much the same thing. So the nail is this thing, round thing in the middle. Got a string, and this is the back of a picture lah. This is the back. So they're asking, what's the tension in the supporting wire? Let's first draw the tension. This picture frame going to have some forces acting on it. Firstly is the weight, right? So I guess the center of gravity, CG, is here, so you can say the weight comes down. What's the weight? 4.2 kg. So 4.2 times 9.81. So I'm just going to put 4.2 G. This G is 9.81. It's not grams. It's 9.81. Okay, then the tension, this picture frame will experience a tension like that and like that. 2 points pointing up. Important to note that these two tensions are the same. So I'm going to circle them and say same. There's just 2 because there's 2 points hanging up. Okay, is that all we know about this question? Okay, so picture on the wall. They didn't say the picture is flying. It's not dropping. It's just there. So you can say it's in equilibrium, which means there should be no net torque, no net force. But in this case, I think it's enough to think about the forces. So let's think about forces. Net force should be 0. The horizontal components should be 0, firstly. Is this true or not? What are the forces that have horizontal in it? Tension only. I redraw the diagram up there. I'm going to get something like this. There's a weight, tension, and tension. Not to scale, by the way. My drawing is not to scale. Okay, you have 25 degree and 25 degree. So the only forces that have a horizontal component to them are tension, and these are equal. Okay, so tension will have, if you want to find, this will be T adjacent hypotenuse, T cos 25. This will be T cos 25. These are the horizontal parts. So yeah, it's 0. Check. How about the vertical? Should also be 0. What's pulling the frame down? Weight. Oh, so we have the weight going down, 4.2 times 9.81. Anything else? Oh no, tension's all pointing upwards. So tension, if I zoom in a bit, this is the T, this is your angle, and you have Ty, which is the vertical component of tension. So what's Ty again? Opposite hypotenuse. So sine. So you can say the Ty is the part going up, so T sine 25. That's for one side of the string. Got another part. So T sine 25 again. Because got two string ma, one tension, one tension, one tension. Although they are technically the same string, but there's two tension forces at play. So you need to remember there's two. So if you want to shortcut a bit, you can just say, oh, it's just 2T sine 25. Also can. So on the left side, 4.2 times 9.81. What do we get for T? Grab a calculator. Divide by 2, divide by sine 25. You should get about 48.75 Newton. Round off to 2 sig fig will be about 49 newtons. So that is the answer for the questions like this. The key thing to remember is if there are stuff hanging on the wall, there's actually two tension forces. Okay, one on the right side, one on the left side. That's where these two come from. Okay, remember components, tension, and things like that. Let's look at something a little conceptual, a little bit more tricky. Now here we have two picture frames. What's the difference between them? Look at the triangle. Ooh. Let's read the question to find out more. So there are two ways to hang the same picture. In both cases, a string is attached, looped symmetrically. Okay, good to know. The forces shown are the forces act on the nail. So all these T and R arrow now is the forces on the nail that's holding up the picture on the wall. The diagram 1, string loop is shorter. Okay, it makes sense. I mean, it does look shorter. The string, by the way, is this. That's a string shorter and this is a longer string. Which information about the magnitude of forces is correct? What are our choices? R and T. Well, we know what T is, but what is R actually? R is the force from the wall on the nail that keeps the nail up. Okay, so you hammer a nail into the wall, boom, 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 boom. You hang something on it, hang a string there, but the wall will kind of keep the nail up, and that's the normal reaction force, keeping that nail up there, not just dropping down. So they say, wow, R1, R2, T1, T2. How do they relate? Let's see. So firstly, let's look at R first. R is basically supporting the whole weight of the picture frame, right? Picture frame is going to have some weight. W. Oh no, it disappeared. And another weight, W. Somehow, the W will have to balance out the tension forces. How to draw the tension? Okay, tension, W. This is the free body diagram for the picture frame. So picture. And those two same tension forces will be the one that pull down on the nail. So this is free body diagram for the nail. And then the nail will experience something to counter it. So the tension forces are basically just intermediary lah. They're just helping to transmit this force in this case. You can think of it that way. So essentially, the reaction force on the nail, if you want to shortcut that way, should be the same as the weight of the picture. That's how it can support the weight ma. If not, how's the nail going to support? So you think I'm going to say, same picture frame, therefore the nail should be, the nail should have the same reaction force in both. That's why it can support the weight of the frame in the first place. So from there we can cancel out C and D. Now we have to think of tension. Do you think tension is the same or not? Pause this video, think about it. Write an answer or take a vote. You think it's A or B, and we'll find out real soon. Okay, so here's how I can think about it. They are not the same. That's for sure, because the angles are different, the lengths are different, so tension cannot be the same. Therefore, what's left is only B law. So we look at B. It says tension 1 is greater than tension 2. Why is that? We'll need some space to draw the diagrams out. So, let's say we have the same R force, which should balance out T forces. T1 or whatever I just call T. Okay. The only thing difference between both is the length of the string, which affects the angle here. Theta, theta. Okay. In the first picture, those two thetas have a very small vertical component. Okay, this red color line is the vertical component, Ty. So, to compensate for that, the tension has to be quite high in the string. So this tension has to be high because the component is very small. But in the other one, wow, the string is much more vertical and have a much larger vertical component. So this tension does not need to be so high because already got vertical component ma. So this is actually smaller. This one is bigger. Let's take a look at a simulation to make sense of this a little bit more. Look at the forces. Here we have a very handy simulation down on GeoGebra. I'll post the link for you all to access down in the description and in Teams also. So you can go play around with it and try to understand this tension thing better. Anyway, here's a similar situation. What I can adjust here is the angle between those things. So in a way, like that lor. Your string is getting longer, shorter, longer, shorter, longer, shorter. Okay. What I want you to notice is there's a misconception that the tension depends on the length directly. Well, actually the tension that depends on the angles, and the angles affect the length. Or rather, the length affect the angles and the angle affect tension. So take note. Firstly, weight is, let's say 12. I can choose what weight I want. 12 newtons down. Which means the components, total component upwards should be 12 as well. So 6 plus 6, also 12. So no matter what angle I change, the vertical component is fixed because we are saying that the system is in equilibrium. So 6 Newton is for sure. So then what is changing? The angle's changing. Look at how the tension changes. Tension change, angle change, tension change, angle change. If I have a very large angle, means your rope is almost vertical, then both of them have a lot of vertical, most of their components are vertical, let's put it this way. So the resultant tension does not need to be so big. But if your angles are very small, most of these tensions components are in the horizontal, so you need a large horizontal in order to have this angle and this tension together. So notice you change the angle. How does it change? Go play with this and look at the patterns and try to wrestle with the understanding and see how you can make sense of it. Another one which I also will post is one way you can just drag around for fun. So this is the same thing. You can click on this object. Okay. Notice how if your string is quite vertical, these two arrows, which are tension, is quite small because a lot of vertical component in it. But if you make the strings quite horizontal, wow, then the tension force becomes much bigger because it needs to compensate for that vertical component to balance out the weight. Okay. See this diagram on the right side? The tension have to add up to be the weight, both tensions. Okay, so the angle affects that, and what affects the angle? The length of the string affects that. Okay, so go play around with these things and you understand better how to work with tension. Our last double tension is this hanging star question. looks like someone's necklace, or it can be the lights hanging on your wall or roof, you know, Christmas lights and all those kind of things. Or it could be just earphones hanging on your ears. Same thing. You know, it's very painful if you drop your phone while you're wearing earphones because you suddenly pull and it's like, ow, my ears. Sometimes you break your earphones. Anyway, so this one, an object hangs by two cords around two rods. It almost looks like a pulley system if you want to think of it that way, double pulley. Object weighs 10 Newton. Oh, we should write that down. 10 Newton. Okay. There's negligible friction. So that tells us something about the pulley rods. Negligible friction between the rod and the cord. Angle is 90 degrees. So the angle is between this one here. Which row of the table gives an angle of 90? Wow, they give us a bunch of values for F. What is F? F in this case is that force there. Okay, let's draw more forces. Look at the F1 on the left side. That is balanced by a tension upwards. T1. Okay, so in this case, T1 equals to F1 lah, just so you know, because it's in equilibrium. Same with the one on the right side, F2. There's a T2 and they are both equal. T2 equals F2. Now, if you think of your pulley stuff, when you go over the rod, it's kind of like a pulley wheel. So you have the same tension 1 and same tension 2, which is also F1 and F2. Here comes the question. What are those forces? 9, 10, 6, 4, 8, how do you know? Now, I want you to do this. Pause the video. Go play around with that GeoGebra app thing, drag the things around, and try to decide which one you think is the correct answer for this case. Okay? Pause it, try whatever method, calculation, play with the simulation, and come back and take a look how to finish this problem. Okay, here's the fastest way to do it. You could use math maybe, but it's very hard because we don't know the exact length of strings. They didn't give it to us, so we cannot do it. Oh, resolve component and things like that. So calculation is hard. There's a way to guesstimate your way, but not recommended. So in this case, what we could do though is draw a vector triangle, like the one we looked at in the previous simulation. First things first, I'm going to move T2 over to this side, something like that. Okay, and this will also be right angle. So what I have now is a T1, a T2, oh, so out of shape, and then the weight. So T1 plus T2 should equal to the weight, so I should draw a weight like that. Why is that true? Because of equilibrium. So if you use vectors, you write it in vector language, you should say the weight vector equals to T1 plus T2. Of course, we will take into account all their components, but this is the main idea what we're trying to do. So we have a vector triangle now. Here's one misconception a lot of people have. They will say, oh, look at T1, the string is so long, therefore T1 must be bigger, T2 must be smaller. No, that's a misconception. Okay, length does not necessarily correspond to angle, to correspond to the tension. This is just a diagram only. It's not a force diagram. So don't say, oh, the string longer means longer tension, larger tension. No. But what we do know is from this diagram, how they relate. Hey, look, it's a right angle triangle, so you can use Pythagoras theorem. W square equals to T1 square, magnitude only, plus T2 square. So you need to check through the table. What combination will give you 10 square equals to what square plus what square? So you can try one by one, or if you already memorize your Pythagoras pairs, that will actually be 8 and 6. So this is out. So 8 and 6, which is which? Which one will have a larger tension? In this case, T2 will actually have the larger tension. So this one will be C. Why is that? Okay, for that we need to go to the simulation, but I'll try to explain it now. T2, that's my highlighter, there. T2 is much closer to the pulley or the rod, whereas T1 is quite far away from the rod. So if this is only for unbalanced angle, so both sides of the angle is different. So if the object is nearer to the rod on the right, then that one will have a larger tension. Why is that? Let's take a look at the simulation again. Welcome back to GeoGebra. Here we are on the mode where we adjust the angle individually. So at first we look at how both side angle is the same, but now angle is not the same on one side. Become like that. So the same idea applies. Okay, let's leave it at this misbalanced angle. The total weight down is 12 newtons. So the vertical components of both tension force have to add up to become 12. So 8.6 plus 3.4 is 12. So no matter what angle it is, okay, you have to add up both. So you see how if the block becomes very close to this second anchor, you need a lot of force over there to tap out everything. Tap out means you kind of take care of the vertical component. If I change it all the way, pretty much this is the only string that's carrying most of the weight. The other string is just chilling over there. We can see this more clearer through this simulation here. So if you're in the middle, they are both sharing the load pretty equally, sharing the weight. But if you move nearer to one side, this string is going to take much more of the vertical load because this string is more vertical. If you move it all the way, this string is pretty much doing nothing because this weight is already taken care of by this vertical tension here, fully vertical. Okay. Now watch carefully as I move this object to the left a little bit. Now as I move to the left, this blue force is getting less vertical, so we'll need the help of the green force to contribute some vertical to it, some vertical component, and then like that lor. So if you're nearer to this side, this force is going to be quite big. If you're right underneath, then it's pretty much this string, you can cut it, nothing will change. Notice how this diagram on the right changes, the triangle forces, as I move the object near to the middle. Okay. At first, the blue force is pretty much the same size as the red, but then it starts to get smaller and the green starts to contribute a little more. Okay. Moral of the story, the takeaway is, if the object is right in the middle like this, up here or down here, both strings contribute equally. Okay, like that, equal. But if you tilt it nearer to one side or the other, then one string will contribute more to the vertical component. And that's all for today about strings and tensions.